Imagine you're standing in your attic on a sweltering August afternoon. The air up there hits like a wall. You're sweating through your shirt, the fiberglass bats are doing their best, and your energy bill is quietly climbing towards something that makes you wince every single month. Now imagine someone hands you a 50-pound bag of ordinary sand, the kind you'd find at a hardware store, the kind kids play in, and they tell you, that bag, packed into the right places, insulates better than anything the modern building industry has been selling you for the last 70 years. You'd probably laugh. Most people do. But here's the thing. There were scientists in the 1950s who ran the numbers, who built the test chambers, documented the results, and wrote up their findings with the kind of careful precision that doesn't leave much room for argument. And what they found was extraordinary. Sand, specifically certain configurations of densely packed particulate material, performed at levels that made the insulation industry deeply uncomfortable. Those findings didn't disappear by accident. They were buried, quietly, methodically, and with significant financial motivation. This is the story of what those researchers actually discovered, who didn't want you to know about it, and what it might mean for the way you heat and cool your home right now. To understand why those 1950s findings were so threatening, you have to go back a little further. You have to understand how fiberglass became the default answer to a question most homeowners never even thought to ask differently. Before the Second World War, insulation wasn't really something the average American spent much time thinking about. Homes were drafty. That was just the way it was. If you were cold, you put on another sweater. If your heating bill was high, well, coal was coal and wood was wood, and you burned what you burned. The idea that you could engineer a material specifically designed to trap heat inside a wall or a ceiling, that was still a fairly novel concept for residential construction. Then the war ended, and everything changed at once. Millions of veterans came home. The suburbs started spreading outward from every city in the country like ink dropped into water. Developers were building fast, faster than anyone had ever built before. Speed mattered, cost mattered. And in that environment, a material that was cheap to manufacture, easy to install, and came conveniently pre-cut in rolls and bats was almost impossible to resist. Fiberglass had actually been around since the 1930s. Owens Corning was producing it commercially by 1938, initially for industrial applications. But it was the post-war housing boom that turned it into a household name. Builders loved it because it was lightweight and it fit neatly between standard space studs and joists. Manufacturers loved it because the raw materials were abundant and the production process was scalable. And consumers, frankly, didn't know enough to ask questions. What made it stick, and this part matters, was the R-value system. The concept of measuring thermal resistance gave the industry something enormously powerful, a number. A simple, printable, marketable number that consumers could compare and contractors could specify. And fiberglass manufacturers were deeply involved in shaping how that measurement system was developed and standardized. By the time the average homeowner in 1955 was thinking about insulating their attic, fiberglass wasn't just one option among many. It had become, through a combination of industrial momentum, marketing infrastructure, and regulatory entrenchment, the only option most people had ever heard of. Which is exactly why the researchers running quiet experiments and test chambers that same decade were about to cause a very serious problem for some very powerful people. But here's where the story gets uncomfortable. Because while fiberglass was cementing its dominance in showrooms and supply catalogs, a handful of researchers, working in relative obscurity without industry funding, without the backing of major manufacturers, were running thermal performance tests that produced results nobody in the insulation business wanted to see. The tests weren't secret at the time. They were conducted through university programs and small independent research groups, the kind of quiet, methodical science that rarely makes headlines. The researchers were studying granular materials, loose fill options, things like vermiculite, certain mineral aggregates, and silica sand. Plain, ordinary sand, the kind you'd find at a construction site or a children's playground. What they found was striking. Under specific conditions, and the conditions matter here, we'll get to those, dry, compacted silica sand demonstrated thermal resistance values that were genuinely competitive with the fiberglass bats being sold commercially at the time. Not in every scenario, not under every configuration, but in controlled attic simulation chambers with proper depth and proper dryness, the numbers were real. They were reproducible, and they were alarming to anyone with a financial interest in selling something more expensive. The data showed something else, too. Something that cut even deeper. Fiberglass, it turned out, performed considerably worse than its R-value rating suggested once you accounted for real-world installation conditions. Compression reduced its effectiveness. Air movement through the fibrous matrix, something the lab tests had largely ignored, degraded its performance significantly. The controlled chamber numbers that formed the basis of those marketable R-value figures, they didn't survive contact with an actual attic. Sand, by contrast, doesn't compress in the same way. It doesn't allow air convection through its mass the way a fibrous bat does. And its performance figures held up more consistently between controlled testing and field conditions. Now, none of this is to say sand is a perfect insulator. It's dense, it's heavy, it adds structural load. There are real practical limitations, and anyone claiming otherwise is selling you something just as hard as the fiberglass industry ever did. But the point, the critical point, is that those limitations were never allowed to be weighed honestly against the benefits. Because before that conversation could happen in any serious public forum, the data started disappearing. The studies stopped getting cited, the researchers stopped getting funded, and the industry that had everything to lose moved quickly and quietly to make sure the numbers stayed buried. So let's talk about how that happens. How does a body of research, peer-reviewed, reproducible, conducted by credentialed scientists, simply vanish from the public conversation? It doesn't happen overnight. It happens the way most inconvenient truths get managed, slowly, systematically, and with a great deal of money pointing in one direction. By the late 1950s, fiberglass insulation wasn't just a product, it was an industry. Owens Corning alone had built an entire post-war economic identity around the stuff. Pink bats were showing up in millions of new homes. Contractors were trained on it. Building codes were being written around it. The R-value system, the very framework the public used to understand insulation, had been developed in an environment where fiberglass manufacturers had significant influence over the testing standards being applied. When the sand test data started circulating in engineering circles, the response from industry groups was not to fund further research. It was to question the methodology, to dispute the framing, to make the conversation expensive and exhausting for anyone who wanted to continue having it. Independent researchers who pushed back found their grant applications quietly rejected. Academic departments with industry funding discovered that certain lines of inquiry were, shall we say, discouraged. Not banned, not censored in any dramatic, documentable way, just deprioritized, defunded, allowed to quietly die. This is how scientific suppression usually works. It's rarely a conspiracy in the thriller movie sense. It's more like gravity. Money flows toward conclusions that protect investment, and it flows away from conclusions that threaten it. Journals that depend on advertising from building material manufacturers develop an institutional reluctance to publish findings those manufacturers find uncomfortable. It's not corruption exactly. It's just incentive, operating at scale over decades. And the result, the practical, measurable result, is that an entire generation of builders, contractors, homeowners, and policymakers made decisions based on an incomplete picture. The fiberglass numbers got refined and marketed and stamped on packaging. The sand numbers got left in filing cabinets. Not because the science was wrong, but because the science was inconvenient. Now, before we get into what this means for your home, let's actually talk about the science. Because this isn't magic. Sand doesn't insulate through some mysterious property that defies explanation. The physics here is real, it's documented, and once you understand it, you'll wonder why no one ever told you. Here's the core principle. Insulation works by slowing the movement of heat, and heat moves in three ways: conduction, convection, and radiation. Conduction is heat traveling through solid material. Convection is heat carried by moving air. Radiation is heat transmitted as infrared energy across open space. A good insulating material addresses all three. What the 1950s researchers discovered, and what has since been quietly confirmed in a handful of independent studies, is that densely packed granular material like sand does something that fiberglass bats fundamentally cannot. It eliminates convection almost entirely. Fiberglass works primarily by trapping air in tiny pockets. The theory is that still air is a poor conductor, so if you can keep the air from moving, you slow the heat transfer. The problem is that air doesn't stay still. Temperature differentials create pressure differentials. And in an attic, where you've got blazing heat on one side and conditioned living space on the other, that air wants to move. It finds paths through the fiberglass matrix, and when it does, your insulation is underperforming its rated value. Sometimes, significantly. Sand doesn't have that problem. There's no matrix for air to migrate through. The granules pack tightly enough that convective movement becomes negligible. Heat trying to cross a sand layer has to do it through conduction alone. And sand, particularly dry, loose-grained sand, is a genuinely poor conductor. The thermal mass also works in your favor. Sand absorbs heat slowly and releases it slowly, which means it doesn't just block temperature transfer, it buffers it. It smooths out the peaks. The combination of those properties, low conductivity, near zero convection, and significant thermal mass, is what the original test data captured. Not as a curiosity, as a measurable, reproducible result. The science wasn't exotic, it wasn't theoretical. It was just sitting there, waiting for someone with money to be interested. Nobody with money was interested. So what does any of this actually mean if you're standing in your house right now, looking up at the ceiling and wondering whether what's above it is actually doing the job you were told it was doing? Start with this. If your home has fiberglass bat insulation in the attic, the kind that comes in rolls, that pink or yellow fluffy material stapled between joists, you almost certainly have air movement working against you. Not because the product is fraudulent exactly, but because it was sold on laboratory numbers that don't survive contact with the real world. A still air test in a controlled chamber is not your attic in July. It's not your attic in January when the wind is pushing against the exterior and pressure differentials are pulling cold air through every gap in the structure. Those conditions degrade fiberglass performance in ways that never show up on the packaging. Now, you're probably not going to go dump a truckload of sand in your attic tomorrow. That's not really the point. The point is that the assumptions baked into how we insulate homes, assumptions that drive billions of dollars in annual product sales, were shaped more by industry influence than by open scientific competition. The best solution didn't win, the most profitable solution did, and homeowners have been paying the energy bills ever since. What you can do is start asking harder questions about R value. That number on the bag or the roll is a best-case figure. Ask what happens to it when air moves through the material. Ask what the effective R value looks like after installation, after settling, after a decade of thermal cycling. Those answers are harder to find because the industry doesn't exactly volunteer them. There are insulation products on the market that address convective bypass more honestly. Dense packed cellulose, for instance, resists air movement significantly better than fiberglass bats. Closed-cell spray foam essentially eliminates it. Neither of them is sand, but both of them reflect a more complete understanding of how heat actually moves, through a building assembly. And both of them have faced their own versions of industry headwinds from the fiberglass lobby over the years. If you're building new, or if you're renovating, you now have context that most homeowners never get. You can push your contractor, you can ask what the installed performance looks like, not just the theoretical maximum. You can ask whether the product has been tested under conditions that resemble actual use. Because the 1950s data didn't just tell us something interesting about sand, it told us something about the gap between what insulation is rated to do and what it actually does. That gap exists in your attic right now, and it's costing you money every single month. So what do you do with all of this? That's the question that actually matters. You start by understanding that the information exists. The 1950s test data wasn't destroyed. It was buried, minimized, and pushed to the margins, but it survived. Researchers have accessed it. Independent building scientists have written about it. The physics hasn't changed. What's changed is how much effort you have to put in to find the honest version of the story. Share this. Seriously. Most people renovating their homes right now have never heard any of this. They're walking into a big box store, grabbing whatever insulation product the packaging says is best, and trusting that the R value on the label is the whole story. It isn't. You now know it isn't. That's not a small thing. Look into your local building code requirements and ask whether they're specifying installed performance or just theoretical ratings. Push that question to whoever will listen, because it's a legitimate one. And if you're a renter, if you don't control what goes in your walls and ceiling, you can still ask your landlord what's up there. You can still understand why your heating bills are what they are. The fiberglass industry spent decades making sure this conversation didn't happen at scale. The least we can do is have it anyway.